So, hello everybody. In case you missed it like literally 2 seconds ago, my name is Dee or Dee Dunne. I am a second year PhD student at Caltech. And while I'm there, I mostly study galaxies. So I study how they grow, how they change over time, how they form. And I also study some really cool special galaxies. And I am here today to tell you about my favorite one of those special galaxies, a type of galaxy called a brightest cluster galaxy. You can maybe guess some stuff about it from the name, but we'll get into exactly what it is in a minute. And these are my favorite galaxies because they are the biggest galaxies in the universe. They are the center of the biggest things, period, in the universe. And they are cannibals. So we will break all of that down as well. But before we get into any of that, we kind of need some context. So talking about clusters of galaxies, what does that mean? How big are they? Where are we in relation to a cluster of galaxies? So we're going to start simple. How is the universe organized? Well, we live on the Earth. The Earth is a planet. The Earth is a planet in the middle of a solar system. It's one of 8. It is orbiting around the Sun, which is a star. The Sun is one of about 100 billion stars in the Milky Way galaxy, which we have here. And that's usually where most people are like, okay, I get all that, we're in a galaxy, and then they kind of stop. And they don't tend to realize that our galaxy is actually part of something much greater. It is not floating through the universe on its own. It is actually gravitationally bound, so clumped up via gravity to a ton of other galaxies in the local group, shown here. And the local group is clumped up with a ton more galaxy groups in this supercluster. You can't see the local group in that because we're taking the picture from the local group. But this is the Virgo cluster. We're a member of the Virgo cluster. And that's not even all. The Virgo cluster is a member of the Laniakea supercluster. So all of that is all clumped together. The Laniakea supercluster is a member of the universe. That's about as big as it gets as a supercluster. So we're going to be talking a lot about clusters of galaxies today, just because the brightest cluster galaxy very intimately linked with the cluster that it's located inside of. So we've established that yes, there are clumps of many other galaxies, but there's a bunch of other stuff going on in a cluster. So we're going to start off with just what is a galaxy cluster made of? And this is an audience participation activity. Yell at me what you think a galaxy cluster is made of.
Galaxies.
Galaxies, excellent. Woohoo! Step 1. So there are about 100 to 1,000 galaxies in a galaxy cluster. But that is only about 1% of the galaxy cluster by mass. So we still have 99% of this thing that we haven't accounted for. Yes? What is a galaxy? Yeah, so a galaxy is a big clump of stars and other stuff. So like gas, stuff we call dust, which is just heavy elements that are heavier than hydrogen or helium, like dust on Earth, dark matter, all of that sort of clumped together and rotating. So it is just so I'll answer this and then we'll do like a heavier Q&A at the end and we can get into it. But yeah, so the solar system is just a single star, and it's a bunch of stuff that is like rotating around that single star. Galaxies are many stars. They're made of many solar systems. So yeah, solar systems are great. They are a key part of how our universe is organized, like gravitationally, but they're just definitionally smaller than a galaxy. So we're working on what a galaxy cluster is made of. We had galaxies. What else? I'm going to go back to this image. We still have 99% of this cluster to account for. I might have given you a sneak peek talking earlier. Dark matter, exactly. So about 90% of this galaxy cluster is this stuff called dark matter. And dark matter is called dark matter because we have no clue what it is. If you're wondering what it is, so am I. We have really no idea. We just know that it has to exist because we see its effects on the stuff around it via gravity. And we know that those gravitational effects mean that about 90% of galaxy clusters have to be made of stuff that we don't see. So Dark matter is a huge part of galaxy clusters. It's really key in sort of the gravity tying everything together. That's about 90% of the cluster. So we still have 9%. Anyone else know what might be in a galaxy cluster? This one's harder. Empty space, that's true. It's not going to count in our mass reckoning, though. Love? Maybe? So, about the remaining 9% of our galaxy cluster is this stuff called intracluster medium, which is jargon. Basically, what it is it's loose hydrogen gas, helium gas, stuff that astronomers call metals, which is anything that's not hydrogen or helium. And this is stuff that's just floating loose in this cluster. So it's not attached to any single galaxy, it's just there. And it is actually very important for how these clusters evolve, which we'll get into in a minute. And then, the final thing, the brightest cluster galaxy, the most important part of the galaxy cluster. It is technically part of the galaxies, but we're going to keep it separate because it's really cool. So, this is a talk about brightest cluster galaxies, and we are here to do science. So I'm going to make you do some science with me. I'm going to flash some images of brightest cluster galaxies, or BCGs as they're known in the business, and I'm going to get you to look at them, and first of all, point out which one you think is the brightest cluster galaxy, just based off of the words brightest cluster galaxy. And then I'm going to, at the end, we're going to sort of figure out what's common between all these galaxies. I'm telling you this is a distinct type of galaxy. Why? So, here's our first BCG. It was on my title slide. Which one is the BCG? Yeah. Not a trick question. Yes, that is the BCG. So look at it, admire it. What are its properties? What are some things that you notice about it? We're going to move on to our next cluster, which is very blurry. Middle, yeah. Once again, here's our BCG. And then our final cluster, exactly. Here's our BCG. Bam. So, we have 3 BCGs. What is similar about these BCGs? Why am I telling you they're a distinct population of galaxy?
They're bright.
They're bright. Excellent. There we go. Luminosity. BCGs are bright. Good work. What else? They're in the middle. That is true, and that will actually be very key.
They're big.
They're big, is what I was driving at. So they're the most massive galaxies in the universe, I said at the beginning. They're about 10 to 100 times the mass of the Milky Way. They're very large. What else?
Shape.
Shape, yeah. What are we noticing about the shape? Does it look like a traditional galaxy?
No.
No, I heard the actual word over here, but yeah, these are elliptical galaxies, which just means they're blobby. They're not the beautiful Milky Way spiral that we all know and love. They're just sort of this big amorphous sort of hunk of stuff. And then there's one final thing that's maybe a little hard to see on this screen. I will prompt. What color are they?
Red.
Red, yeah. They're white, but they're redder than the other galaxies around them. This is sort of an astronomer thing that I'm going to tell you and you're going to have to believe me. Yeah, BCGs are red. So, why? We've done step 1 of science, we have observed. Step 2 is to figure out what's going on, what's making this happen. And so, in order to do that, we're going to actually have to go back to the beginning. So I said that BCGs and clusters are really linked. We need to understand how clusters form in order to understand how BCGs form. So, this is the baby picture of every cluster in the universe. This is the cosmic microwave background. And you may notice that there's some red clumps. These red clumps are just areas of the universe that happened to be denser than other areas at the time when the universe stopped being this like rapidly expanding soup and started to be actual stuff. And so these clumps, because of gravity, got even clumpier as time went on. That's sort of history of the universe in 2 seconds. And so we're going to see if this works. Here's a beautiful video from the illustrious simulation that may never load of the evolution of the universe. We'll wait. I'll tell you what you're gonna see, and you can act appropriately odd even if nothing happens. So what you're going to see is you're gonna see a bunch of red gas that's just sort of floating loose, in the universe. And you'll see that this gas is moving into certain regions. It's sort of congregating on different parts. That is the formation of galaxy clusters. So right here, we have what was one of those red clumps in the cosmic microwave background baby picture that I showed you. And you can see gravity is pulling all the other stuff in towards that even more. And you can also maybe see, the resolution's really bad, that parts of it are sort of really bright dots that kind of have tails. Those bright dots, it'll resolve in a second to the stars instead of the gas. And those bright dots are galaxies. Here we go. So you can see that those galaxies are congregating on those original clumps. And that is how galaxy clusters are made. They started being clumpier than the rest of the universe, and gravity did the rest of the work and pulled everything else towards them. So, if we go back to our, picture of a galaxy cluster, this is what I was showing you earlier. It's sort of this clump of dark matter and intracluster medium with galaxies floating in it. What I'm going to show you is sort of a representation of the mass in the cluster, so we can work with the gravity in sort of a 1D way. It's kind of like this. So this is the heaviest part of the universe. You can picture all the other stuff is falling into the heaviest part, like a pit or a well. Astronomers like to see a gravitational potential well. All that means is this is really heavy, it's really low down, gravity's pulling stuff into it. So there happens to be one galaxy at the center of this well. It just got really lucky when it was formed. It lied right on top of this sort of really dense region of the universe that all the other stuff is falling into. And so all the other galaxies are getting pulled towards that center by gravity. So that's maybe dangerous for them. Maybe they don't want to do that. But they're getting pulled in. There is something that might save them. So this is 1D, so you can't really see it. But as these galaxies are falling in, they're also spinning around. It's kind of like one of these coin vortex machines. I don't know if anyone's ever seen those. It's kind of hard to see too, but it's like you drop the coin in and it whizzes around for a while before it finally falls in. Galaxies are doing that too. It's the exact same physics where angular momentum is keeping them moving around instead of falling directly in. That's kind of what's going on. They kind of want to keep spinning. That's kind of helping them out against the gravity that wants to drag them in towards the BCG. So, centrifugal force is being nice to them. But then, we've got this intracluster medium that I mentioned. This 9% of the cluster by mass. And that is the friction that is working against the centrifugal force keeping them away from the BCG. We call it dynamical friction, but it's the exact same stuff as that coin machine that's slowly bringing the coin toward the center. This is slowly slowing down those galaxies from flying around and not falling into the BCG. And it's slowly slowing them down so they start to fall in. And all of a sudden the gravity wins, and this happens. If it'll play. There we go. Once again, this may never load. Yeah! So we have what is called a galaxy merger. The two galaxies slam into each other, and they eventually merge and become one. And one of them is slightly bigger, and all the other stuff from the slightly smaller galaxy ends up where the slightly bigger galaxy was, and we call it part of the slightly bigger galaxy. So the slightly bigger galaxy gets even bigger. The slightly smaller galaxy disappears. So the slightly bigger galaxy is eating its friend. It is taking all the stuff that made up its friend and just bringing it into itself. And we call that galactic cannibalism. So that is what a cannibal galaxy is. That is what it does. It has grown bigger by accreting, by gobbling up its neighbors and its friends. And that is how BCGs grow. That is how you get a BCG. So if we go back, oh yeah, I almost forgot the most important part of this talk. So you can kind of think of BCGs as sitting at the center of the Sarlacc pit from Star Wars. So they're sitting at the center of this pit. This cluster is slowly taking its friends. It's taking the Luke Skywalkers of the cluster world, and it is slowly feeding them to the BCG, and all the BCG has to do is just sit there and grow, and keep gobbling things up and getting bigger and growing and growing. And that is how you have a brightest cluster galaxy. So, we had this list of properties before. We've kind of accounted for 2 of them. So, they're really big and they're really bright because they have sat there and they have ate up all of their friends. They've been slowly fed to the BCG by the cluster. This actually also accounts for point 3, the shape of the BCG. It might have started as that beautiful spiral, but as all these other galaxies are like slamming into it and moving it around, it's like not a very peaceful Sarlacc feeding, I guess. And so that's making it sort of bigger and fuzzier and more elliptical. That lovely spiral structure can't stay. But the final thing, the color of the BCG, that we haven't really accounted for. So we're going to explain that now. And in order to do that, we kind of need to get into why galaxies are certain colors. So we've got this image in the background. You can see this galaxy is really blue, that's kind of red, that's blue. Why does that happen? Yeah, exactly. So what happens is when stars are made, there are a bunch of different kinds of stars that can be made, and there's sort of 2 broad classes. You can either make a really big star, and these really big stars, they burn fast. They sort of live fast, die young. They burn really hot, and because they burn so hot, like, you know, a flame on the stove is hot when it's blue, they look really blue as well. So those are blue stars, and so when a galaxy is making a lot of stars really fast, they look really blue because there's lots of these sort of bright, young, active stars. But then those stars, they die off really fast. So fast that we actually sort of, as soon as star formation stops happening, as soon as it stops actively making new stars, they almost immediately start dying. And we're left with mostly just these red stars that started smaller and cooler, and they can live for much longer because of that. And so the galaxy looks red. And so basically the color of a galaxy is sort of telling you how fast that galaxy is forming stars, because it's how many of those sort of live fast, die young, bright blue stars that we see. And so the reason that the BCG is red then has to be that it's not making new stars. And the reason that that is happening is because none of the fuel that makes stars sort of survives the journey into the center of the cluster. And that's for a couple of reasons. Reason number 1 is these galaxies out here that aren't quite in the cluster yet, they're actually connected to the rest of the universe. They're sort of constantly being fed gas, which is the fuel that makes stars, from the rest of the universe. You can see it's blue here, it's spiraling in. But once those galaxies fall into the cluster, they're cut off, they're isolated. And so that gas is no longer falling in onto the galaxy, and so it no longer has the fuel to make new stars, and we call that strangulation. So these are the actual technical terms, I promise. So strangulation or starvation is the first thing that happens to galaxies when they start entering these clusters. The second thing is, as this galaxy is falling in, all the other galaxies around it are also falling in, so they're getting much closer, and they start sort of bumping into each other and shoving each other around, start fighting. Here's some pictures of them actually doing that. You can see they're kind of ripping each other apart. Even if they're not fully merging, they're still disrupting each other. And that is also sort of knocking away the fuel that makes stars. It's affecting the nice efficient star formation that was going on. And we call that harassment. So that is also happening. We've got 2 things stopping star formation. And then the final one is, as these galaxies are falling into the cluster, they start rubbing up against all of this intracluster medium here, this 9% by mass. That's actually really important. Because what it is it's just this gas that's just floating there, and the galaxy's coming in really fast and it's smacking into that gas. And sort of all the loose stuff in the galaxy, it's not staying together with the rest of the galaxy once it smacks in, it's sort of knocking all the loose stuff out. And so we're just left with the stars and the gas. The gas is like knocked out of between the stars, because the stars are massive enough to stay together, the gas is not in the galaxy. So we end up with these sort of green blue kind of tails coming out of the galaxy. We call these jellyfish galaxies. That's kind of a nice name to interrupt all of our violence here. But these are another way that galaxies lose their mass. That was an illustration. Here's two actual ones. You can see the gas tails coming off. The galaxy's coming into the cluster this way. The gas is being left behind it. And this is called ram pressure stripping. So, between all of that, between our strangulation, our starvation, our harassment, and our ram pressure stripping, by the time the galaxies make it to the BCG, all of their gas, all of their fuel is gone. They just have stars, they just have the old, sort of lame, like the really stringy old meat kind of to be fed to the BCG. So that is why BCGs are red, is because none of the like young active fuel and the young active stars actually make it down there. So there we go. That is the brightest cluster galaxy. That is why they are cool. That is why they look the way they do. So the last thing we have to do as scientists is sort of justify, why do we care? So what? Why am I here talking to you about this, other than it's cool? And there's lots of things that BCGs can be used for because they're so intimately connected with the cluster around them. And because clusters are the biggest things in the universe, and they started out as those biggest clumps in that sort of cosmic microwave background baby picture I showed you, that's all like really important for understanding how the universe evolves. So BCGs help us understand the history and evolution of the universe. They also help us understand how stars are made, because they're sort of in an environment that's been like artificially cleaned of all of the like original star formation. If any new star formation goes off, it's really like sort of pristine, and that's interesting to study. And then finally, they're in a very extreme environment, and we want to know how different environments in the universe affect how galaxies grow. So that's the like scientist reason for why we care about BCGs. My reason is they're cool. So thank you very much. I will take questions. Yes, Ewan.
Is there some sort of like, I think you were finding it from the talk, that was really cool, but I was wondering, like, is there simulations that show us BGBs taking over, like, slowly but surely everything? Like, if they just keep combining, is there like a limit to how much species we become before they'll never combine?
Yeah, so the question was, are there simulations that sort of show how these BCGs form? And then another really good question is there a limit to how much mass they can take in? Will they eventually sort of stop being fed by the universe? That was the question, right? So the simulations, yes. That one I showed you earlier. We're gonna go back through slides really fast. So the first thing I showed was a simulation of clusters being formed. And the BCGs sort of form just by consequence. They kind of just have to. Is there a limit? Is a question that is a little bit more of a cosmology question. Because gravity is just going to kind of keep feeding these things into the BCG. And it's something that it likes to run away. Like the more the BCG is fed, the heavier it is, the heavier the center of the cluster it is, the more attracted all the other galaxies are to it. What's going to get in the way eventually is the universe is expanding constantly. And eventually that will happen so much that it'll be ripping clusters of galaxies apart, because they're sort of the biggest thing in the universe. They're the first thing that will be affected by it. And so eventually that will get in the way. So it'll be a race between how big the BCG can get before the universe starts to rip the cluster apart. And I don't actually know what that specific point would be. Yeah. Yes.
I thought that the reason why those galaxies are pretty red, because they're farther away, they're moving away.
Yeah.
Redshifted, as opposed to like the age of ages to a star age. Is that really just two ways of seeing the same thing, or?
So the question was, they thought that galaxies appear red in images like that because they're really far away, and because the universe is expanding, they're being moved away from us, and they're Doppler shifted to redder wavelengths by the expansion of the universe. The answer is both are happening constantly. So when I say that a galaxy is red in a galaxy cluster, they're all moving away at the same speed, and so it means that it's red relative to its neighbors. So it's a separate effect from the galaxies further away. So both are happening at the same time, and you need to sort of figure out what is the thing that is making your specific galaxy appear red, but there are ways to tell. Yeah?
Okay, in our local cluster, so Andromeda will be the center of the mass, right?
I believe so, yes. Yeah. So the question was, in our local group, is Andromeda going to be the center of mass? Yes. It will eventually fuse with the Milky Way galaxy in one of those galaxy mergers, and we'll create a galaxy called Milkdromeda, which is a very unfortunate naming that I do not like. But, yeah. Anything else?
Yeah. Team Milky Way.
All right, I think we're gonna, oh, yes. Yeah. Sorry, I was right by the speaker and it scared me. The question was, why is the cluster named for Virgo? And the answer is just because the center of the Virgo cluster from Earth appears in the middle of the Virgo constellation. Yeah. So we're technically part of it, but from Earth, the center looks like it's in Virgo. Yeah. All right. So I'm being cut off here.
Please thank Dee Dunne. Great talk, Dee.